All right, we are going to go through the last few pages of the notebook. This will cover integrating to find the voltage due to a continuous charge distribution. We're actually going to start off with the harder examples first, and then they'll get easier as we go on. This first one is a problem that's above AP standard. You're not expected to know it. We're looking at it here because we've seen this before when we integrated to find the electric field. And we know that there's a relationship between electric field and voltage. Electric field is the negative derivative of voltage with respect to position. And we can find voltage here and then use the voltage to find electric field and see if it agrees with the result that we got last unit when we integrated the electric field elements to find the electric field. So here we'll find voltage and then we'll use voltage to find electric field. Of course, you might want to use voltage on your own, just, if you needed voltage for something. But a good way of checking these is using the voltage after we got it to try to find the electric field and making sure that agrees with the results we got from last unit. One thing to keep in mind when we're doing this is that voltage is not a vector. So there's no components to cancel out. When we looked at this kind of problem previously, if this was a positive line of charge, we would have had an electric field element that pointed from this dy right here. We'd have an electric field element that pointed this way, kind of down and to the right. And from down here, we'd have an electric field element that pointed up and to the right. And the y components of those two cancel. And we just needed to add up the x components. And to find the x components, we would take the cosine of this angle. We don't need to do that in problems that involve voltage because there are no components to cancel. Right? Components are only for vectors. No vectors here, no components, no canceling. Our charge density is our charge divided by the length. Charge per unit length is lambda. Sigma would be charge per unit area. Rho would be charge per unit volume. So for any individual charge, the voltage for a point charge is V equals KQ over R. So here we're going to have dV equals K dQ over R. And this would be the voltage due to the ith charge element. This would be the charge associated with that, and this is the position from where you are calculating the voltage to that ith element. When we add all of these little elements up, we'll integrate. That'll give us the total voltage at point P, K dQ over R, and this R corresponds to wherever that charge is located. K is a constant, dQ is lambda dy, and R is the square root of x squared plus y squared, right? That's our distance here. And we're going to integrate from y equals negative a up to y equals positive a. So that's our integral. K lambda comes out. There's our integral. That integral is non-standard. I looked it up in the... Well, first I used Wolfram alpha, but that didn't give me a particularly pleasant result. I also looked it up in the back of the book. I know, old school, right? You actually use your book for something. But what I found was that the result in the back of the book was simpler than the one that I got using Wolfram alpha. And I checked it on a couple of other reference pages online, and I found the same thing. So I don't know. I wasn't typing anything incorrectly into Wolfram alpha, but I'm not sure why it gave me a result that wasn't quite as user-friendly for this. So never pays to double check your sources. Maybe there's an easier way of expressing something out there that you wouldn't know about until you check it out. So we're evaluating this from a to negative a. This integral here is not something you're expected to know. If you ever encounter an integral that's not familiar, look it up, right? So when we evaluate here, we're going to get the ln of all of this stuff with a, and then subtract the ln of all this stuff with negative a. When you subtract two logarithms, we can use the property of logarithms that turns it into a division. This a squared here would be a negative a squared, but of course negative a squared is just a squared. And I substituted back in for lambda, q over 2a. Now to find the electric field, we're going to take the negative derivative with respect to x, because our electric field, we're expecting it to point to the right. And there's no components in the y direction or the z direction out of the page or into the page. We can see that this is not going to have any components in the y or z directions because there's no y or z variables in here. So when you take the negative derivative with respect to y, you'd get 0 because this is constant in the y direction. When you take the negative derivative with respect to z, it would be 0 because this is constant in the z direction. The only way this varies is in the x direction. Take the derivative, kq over the quantity x times the square root of x squared plus a squared, and that agrees with the result of last student, which we're going to check out right now. So this was a partial line of charge, which we had, where was it? Here, right? Partial line of charge. Now, you have to be a little bit careful here because this has length L, ours had length 2a, right? So anywhere we'd have an L, we'd have to put in a 2a. This would be a 2a. This would be a 2a. When you square 2a, you get 4a squared. There's a 4 in here that could get factored out as a 2. That would cancel with this 2. Lambda here was given in our problem. Lambda was q over L. So there are some differences, but you can see the basic thing here. X square root of x squared, and remember this would become 4a squared and that 4 would come out. So it does have the same behavior as what we saw before, which it absolutely should. Our next one, things are going to get a little easier here. We are looking for the voltage at the center of this arc of charge, the center right here. Now, unlike the electric field where we had to integrate over the angle because we had components that will cancel, components don't cancel with voltage because it's not a vector. It doesn't have components. So all we need to do is figure out what the voltage is from each little spot along the way here and add them up. The thing is, all of these spots act the same as far as voltage. They are all the same distance away. And every little spot on here, because our charge density is uniform, right? It's not like one end of this has more charge than the other end of it. It's not like our charge density varies with angle or anything. We have the same amount of charge here, 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 same amount of charge spread evenly over this. Because of that, it's going to make integrating really easy. So the voltage at point P is the integral of kdq over r. R is a constant, which in our problem is a. K is a constant, so we can pull k over a out. And then we're left with the integral of dq. But dq, when you integrate that, you're just going to get the total charge of 2q. So that's it, just 2kq over a. Very easy to find the voltage at the center of this. Way easier than finding the electric field. Now, we know the electric field points down at this location. If this is positive charge, electric field points away from it. Can we find the value of the electric field here by differentiating? Well, if we try that, and I put this with respect to y because it points down in the y direction, 2kq over a does not depend on any variable. And so it's not a function of y. And we can't find E by taking the derivative of this, because it's just, this is just a constant amount, and we don't know how this voltage would change in space. It does change in space. It's just that this expression doesn't tell us how it changes in space. Next one, ring of charge at some point P over here. Now you could use the same technique that we just used to find the voltage in the very middle. It would be the exact same integral. You would just have a full ring instead of half a ring, but you would still end up with this integral of dq, and you'd still end up with the total charge over there. Here, our distance from P to our little charge element is x squared plus a squared, right? The hypotenuse of that triangle. R is still a constant though. Every spot on this is the same distance away from point P, and we don't need to cancel out anything. No components, because it's not a vector. So KQ over R, and we just substitute for what R is. Right? Square root of x squared plus a squared. Now if we want to try to find the electric field at point P, if this was a positive ring of charge, the electric field would point to the right. And this is a function of x. So when we take the negative derivative with respect to it, we will get a meaningful result. KQX over x squared plus a squared to the 3/2 power. Let's compare that with our result from last unit. This was the ring right here. Look at that. This one we got from integrating, and remember we had to multiply by cosine of the angle here to cancel out components. KXQ over x squared plus r squared to the 3/2 power. R here is the radius of our ring. In the problem that we were just looking at, the radius of our ring was a. So this is the same result, just with variables that fit our problem. Now when we look at the disk here is a sum of many, many rings. So I'm going to take this result of voltage from one ring, and what we want to do is integrate and find the combination of all the rings, starting with radius 0 up to radius r. Now I've adapted this for this, adapt this result here for this problem. There are some differences between these two diagrams. Look at this. We are still a distance of x away from the center, but the radius of this ring was described with the variable a. The radius of this ring is described by variable little r. So where I had an a here, I've replaced it with a little r. And we need to know how much charge dq is on one of these little rings. Well, if you take this little tiny ring and unfold it, you get basically a rectangle whose one dimension of that rectangle is the circumference of this little ring, and the other dimension is dr. The disk has charge density sigma, which is going to be in coulombs per meter squared. And this is what you get when you unfold that ring. And the amount of charge on that ring would be sigma, our charge density, times the area of this ring, which we're modeling as a rectangle, which we're entitled to do because it's very, very, very small. And so the inner circumference and the outer circumference are the same, so it'll form a rectangle because it's so small. So I substitute in for dq. I can pull out constants. What are my constants? 2 pi k sigma. I'm left with the integral of r dr over square root r squared plus x squared from 0 to r. This integral is easier to perform, and when we evaluate it, we get this expression for the voltage at point P. Now, if we want to find the electric field as a way of checking our result, take the negative derivative with respect to x, and we end up with this. Take a close look at it here. 2 pi k sigma, and then 1 minus x over the square root. If we go back to last unit's results, this is for the disk. Here's the disk. Now, our result was just 2 pi k sigma. We see 2 pi k sigma, and then in our parentheses, we had 1 minus x over this stuff. But if you distribute this x inside, right here, x over x, this would be 1, and then I would get x over this stuff. And that is exactly what we have here, right? 1 and then x over. So this is in agreement with the results from last unit. And upon seeing so, you are experiencing a warm and fuzzy feeling because all is right in the world. That's at least one thing physics is good for. All right, so there's some examples of integrating to find the voltage. Now, if we look at some situations involving conductors that we know something about, like a spherical conductor, we know the electric field of a spherical conductor from Gauss's law. We can apply what we know to find the voltage based on the electric field. So a couple of words here at the beginning. When conductors are in equilibrium, they are going to have the same voltage everywhere in a conductor. Conductors, equilibrium, equal electrostatic equilibrium, right? So charges aren't moving. The entire object has the same voltage. Why does it have the same voltage? Because if the voltage changed, that would be an indication of an electric field. And we know that electric fields do not exist in conductors when they are in electrostatic equilibrium. In an insulator, though, you can have an electric field. And the voltage might be constant or it might not. That depends on if the electric field is even there or whether the electric field is constant or not or anything else. So when we look at a sphere, this is a positively charged sphere here, we know that the electric field for the sphere behaves like that of a point charge when you're outside of the sphere. Gauss's law gives this as a direct result. And remember, K is 1 over 4 pi epsilon naught. So this is KQ over R squared. It's just that they didn't write it with a K. So we get KQ over R squared outside. And on the inside, we have no electric field. For voltage, when you integrate this, and that's what voltage is, it's the negative integral of the electric field with respect to position. Electric field is the negative derivative of voltage. Voltage is the negative integral of electric field. Any relationship that involves a derivative or an integral, you can write it in the other form. If you know an integral relationship, you can rewrite it as a derivative, and vice versa. So here, this is the integral form of the relationship between voltage and electric field. We're going to integrate from infinity to some radius r. We get KQ over r when we do, and K is 1 over 4 pi epsilon naught. So the result that we get matched what was over here, right? Now, let's take two conductors that are connected with a little wire here. Okay? And we want to determine which of these conductors has the greater charge density and the greatest overall charge. Now, the principle here that we're working off of is that any objects that are metal, and these ones are considered to be one big object because they are connected by another piece of metal. Okay? So even if you take two separate objects and you connect them, or you have two metal objects and you touch them together, we're going to treat them like one metal object. Because for the purposes of charge, the charge can just flow as long as they're touching, and the charges would experience it like one object. So this is one object, and one object should be at the same potential, the same voltage, okay? Because if it wasn't at the same voltage, that would mean there's an electric field. And we know that conductors in electrostatic equilibrium cannot have an electric field inside them, so they have to be at the same voltage. So the voltage of A is the same as the voltage of B. That's the starting point. So conductors have the same voltage at all locations when they are in equilibrium. Voltage A equals voltage B. Now, these are two spheres. So I'm going to take the result from above, and I'm going to get KQA over RA equals KQB over RB. I rearrange this. The K's cancel out. And if I move QB to the bottom over here and I move RA to the top over here, I find that the ratio of charges and ratio of radii are opposite. So because radius A is bigger, right? Sphere A is bigger than sphere B. What we find is that there's more charge on A than on B, right? If the top is bigger here than the bottom, the top must be bigger here. So the charge A has to be bigger than charge B. Now, we can look at what happens with electric field as a result of this. Okay? For a conductor, all of the charge is going to reside on the surface. So when we talk about a charge density, we don't want to use a charge volume density because the charge doesn't exist over a volume. The charge exists over the surface of the sphere. So we're going to use sigma for a surface area charge density, and that's our charge over the surface area of the sphere. So we have a sigma A for the charge density of A and a sigma B for the charge density of B. And if you take those charge densities and multiply it by the surface area, you get the charge. So I'm going to take these results and substitute it in here for QA and QB. QA, QB. Now, the 4 pi's cancel. And if I took this RA squared and moved it onto the bottom over here, RA over RA squared would leave me with an RA in the bottom. And this RB squared, I put it on top. One of those cancels with one of those. I'm left with RB on the top. And here I have sigma A over sigma B. Now, although charge A had a greater, sphere A had a greater charge on it, it turns out that sphere B actually has the greater charge density. How do I know that? Because RA is bigger than RB. Sphere A is bigger, so the radius of A is bigger than B. Bottom of the fraction is bigger than the top, means bottom of the fraction on the left has to be bigger than the top. So sigma B has to be bigger than sigma A. Greater charge density. And sphere B is going to have a stronger field near the surface. Another example, we have conducting shells. Okay, these are going to be conducting spherical shells. 300 nanocoulomb charge in the very middle. That means negative 300 here and positive 300 here. This was a neutral shell with a point charge inside. So a neutral conducting shell with a point charge inside. Make that clear. With point charge inside. So the voltage outside here, we can find from Gauss's law. We know the electric field outside here is proportional to the charge enclosed. And so voltage negative integral of the electric field, and we're coming in from infinity, and so we get 2700 over R when we plug in, and I plugged in numbers here for K and for Q, right? So that's what I get, 2700 over R volts. R is the distance from the center, and R has to be greater than 1.2. Then the entire shell here is at the same potential, right? So I plug in 1.2, I find the voltage on the surface, and that voltage on the outside surface is the voltage of the entire thing all the way through. Now, on the inside of this here, my electric field has the same equation, but I am closer now, I'm at a smaller radius, so there's going to be a jump right here in voltage. Actually, maybe I said that wrong. There won't be a jump in voltage. Basically, if we're looking at energy per unit charge, potential energy per unit of charge, if you imagined bringing a charge in and the work that you have to do to it, because the work is related to the potential energy, you'd have to do a bunch of work to get it to here, no work to get it across the shell, and then more work to bring it closer. So if we're finding the voltage on the inside here, it would have to be equal to the voltage that it took to get to here plus the voltage that you're going to change once you move across the inside of the shell. So this was when we're inside here, we have to consider all of the voltage that it took to get to the shell. There is no electric field inside this shell. And so from 1.2 down to 0.8, no electric field, no change in voltage, so that integral goes away. And then we add to that the integral from the stuff on the inside. You can see how that works out. We end up with 5625 minus 2700 over R, and that would be volts, and that would represent the voltage inside this shell here from the center out to 0.8 meters. If you try plugging in 0.8 to this, you get 2250 when you plug 0.8 into this, which is what we should, because we know that the inside surface should have the same voltage as the outside surface, which was 2250. Our last example, I think, is a insulating sphere with uniform charge density rho. When you're outside of here, the sphere acts the same as a conductor. It acts the same as a point charge, so our voltage is kQ over R. Q is rho times our volume. Our volume is 4 pi, our 4/3 pi r cubed, right? Now you'll notice here that this has a K and this one has an epsilon naught. I could write this the other way around. Maybe that'll be easier and just be more consistent here. So K, and then Q was 4 pi big R cubed over 3 little r. And I guess if we want to be consistent, I could put that out in front. 4 pi K R cubed over 3R. Either way, right? I mean, K is 1 over 4 pi epsilon naught. So it doesn't matter how you write it. Either way works. Inside of here, okay, inside of the sphere, we can use the result from last unit. I'm not going to go through it here. You did this in the notes, Gauss's law for a uniform charge density sphere, insulating sphere. This is the result that you get. The way that we did it last unit, we probably had K, but you know the conversion. K equals 1 over 4 pi epsilon naught. The charge that's enclosed would be our density times little r. So we have to, when we're talking about the voltage inside of here, we have to consider, you know, how the voltage is up to the surface and then moving in from the surface. So we split up our integral. This is the voltage from infinity to the surface, and then this is going to represent the voltage inside the sphere. So we end up with this, and because this problem was given with charge density rho, you don't need to substitute in here like Q over, 4/3 pi r cubed or anything like that. This is in terms of the given. And of course, I used epsilon naught. You could just as well put a K in there. Epsilon naught is 1 over 4 pi K. And that's that. So, get that stuff copied down, and we'll see you soon.